Good morning, everyone. So for those who came to Uppsala for the first time, I have to say that you're very lucky because it was the biggest snow I have ever seen in the past 6 years after I came to this place. So my group is working on the field chemistry of electrochemical systems with atomistic simulation, so both physics-based and also machine learning-based. So a large part of results which I'm going to present come from the work done by Yunqi, Lisana, Linnea, and also Thomas. So we are doing, I call it application-driven method development, which means that we usually start with a class of materials which has a common and solved physicochemistry problem. And then we try to develop the theory and method and computational tools to solve that. And for today, the class of the materials we have looking at in the past few years is this electrified metaloxide surface in aqueous solution. So this type of surface exists ubiquitously in electrochemistry, geochemistry, as well as correlative science. And then there are recent experimental advancements which can look at such interface more directly. For example, in the Jörg Diebel's group in Vienna, they developed these apparatus which can dope liquid water into the UHV chamber. And then you can pump in different type of gas and then change the pH and see how the oxide surface would evolve over the time and without actually the contamination. And then we also know that this type of system are often used in electrochemical energy storage, which involve the cation-coupled electron transfer. For example, in the supercapacitors, which provides a timely need to investigate such type of systems. And in contrast to metal, the surface charge of metal oxide comes from the acid-base reactions. When the oxides in contact of aqueous solutions, so there will be the proton transfers between the surface touchable groups with the solution. So when the pH of the environment solution goes above so-called point of zero charge, then the surface will deprotonate it when you get the negative charge. And then when the environment pH goes below of the point of zero charge, then the surface is get protonated. That bears a positive charge instead. And then for metal oxide, during its working conditions, is not at the point of zero charge, which means that the metal oxide is electrified. And then electrified interface will attract counter ions from solution to form so-called the protonic electrodouble layer. And as you can see, for this process, if you want to model it, then you have to handle the surface acid-base reactions. And also, when you have the electrodouble layer at the surface, it creates a strong electric field, which will require to treat properly the polarization environments. And we also want to look at the reactivities. That's why so the method of choice for us is density functional theory-based thermodynamic simulations, so the DFTMD. And if you have ever actually practiced to run the DFTMD simulation for condensed phase systems, then the next question is, what really can fit into the box of your simulation? And we know that for the semiconductor electrolyte interface, there are at least 3 contributions to the final electrodouble layer. So because of the charge transfer between the metal oxide and the electrolyte, you could have the so-called space charge layer, which sit on the solid side. Then you can also have so-called the Guy-Chapman layer, which due to the diffuse double layer, and then this will, of course, will also contribute to a final capacitance. And then we know that under so-called the flat band condition and the higher ionic strength, so both the space charge layer and the Guy-Chapman layer can actually be taken out. So what is left is so-called the Helmholtz layer, which is spans for few Ångström in width, and that is actually the target which we can model with the DFTMD simulation. And then the next question is, how you actually build up your supercell model? So there are at least 2 ways you can do it. So one way is that you actually can charge the 2 sides of the oxide, since the system is under the periodic boundary conditions. You have 2-side oxide. And you can charge them with the same amount and same type of proton charge. So in this case, you can see that you would have two doublers which point to the opposite directions, which gives you a zero dipole in the system. But the drawback by doing that is that when you change the surface charge density, you have to also change the number of counter-ions in your solution, which is going to change the chemical composition of your system. That is not the best choice you can do if you want to do a total energy calculation in DFT. And then instead, what you can do is you can do so-called asymmetric setup, which I'm showing on the screen. So in this case, the two sides of oxide bears the same amount, but opposite type of proton charge. And then what happens is that you have these two double layers which point to the same direction, and that creates a nice polarization in the system. So now we have a new observables from the simulation, which is the supercell polarization. So how this quantity can be connected to the Helmholtz capacitance, which is a key parameter described the structure of your double layer. And before I show you the result from our DFTM simulation, so what we have done is that we actually built up a classical point charge model, which I'm showing here. So the insulator was replaced by these dummy charged walls, where the vacuum here is a perfect sort of insulator, and the rest of the supercell is filled up with electrolyte solutions. You can run a classical MD for such a system and look at how the electrostatic potential looks like. So that is shown at the bottom of the panel. So you can see that there is actually a strong electric field in the insulator region. And we know that from the Gauss law, so a closed body with no net charge, then there should be no electric field outside. But that is not the case we actually see here, which means that electrodouble layers, if you just stake your system directly using this setup, would be uncompensated. In other words, this is actually a sign of a strong finite set effect. So the question is how you actually can get rid of this finite set effect from your simulation. So what we have done is that we actually built this pairwise continuum model, which show on the right, and try to solve it within the periodic boundary condition and to try to find out how the electric equation of state looks like. So by doing this exercise, just to make the long story short, what we find is that if you run with the standard PVC, then there is actually a contribution to the total capacitance, which is due to insulator, our oxide. And that's exactly the finite side effect, which I just talked about. But instead, if you switch your electric boundary conditions from the constant E to constant D, which is the complement thermodynamic variable, then what we have shown in our work is that now the final capacitance only contains the Helmholtz capacitance, which you're interested of. So we find out the formulas actually to compute the quantities. Then the question is how you actually do the simulation. So this has to go back to this seminal paper from Stingel, Spalding, and Vanderbilt. So they devised this constant electric displacement Hamiltonian to look at the ground state ferroelectric system. And what they have done is they actually did this Lagrange transform from the equation 2. And then through the derivation, you can actually show that you can arrive at the equation 1, which is constant D Hamiltonian. So how you actually get your head around about this between the difference of the E and D when it comes to the simulation. So here in this illustration, this shaded area is your simulation system under the PVC. And then we have this electrode. And this electrode, they are the electrical boundary conditions at infinity. So when you run the constant E simulation, the system is under the constant potential. That's why when the E field is 0, your system is under the so-called the short circuit condition. And then the corresponding constant D setup is actually corresponding that you have this virtual electrode, which provides the constant charge. So taking that in mind, so with great help from Jörg Hutter, so the method was implemented into the CP2K. So you can, when we applied to look at the TiO2, 110, and sodium chloride electrolyte system. So you can rate the setup of the configurations and also functionals from the slide. Here what I want to bring your attention is about how actually the supercell looks like. So you can see that on the right side of the supercell, you have the bridging oxygen, which is get protonated. So this gives you the positive charge. And then on the left side of slab, the absorbed water is deprotonated. So this gives you a negative charge. And And in the formula which I showed you before to compute the key quantity, which is the Helmholtz capacitance, so the observable that you need is the supercell polarization. And then the question is, can you actually converge this quantity, right, within the time scale of usual DFTMD stimulation, which is a couple of tens of picoseconds. And we also know that when there is no surface charge, then there will be no net polarization in the system because the system is symmetric. So this serves as a critical test to see whether actually the method would work. So you can see from the panel A, when the system is under the point of zero charge, if you start with your simulation with a standard PVC, that corresponding to E bar equals 0, you start with certain points of your total polarization, and then the system relaxes very slowly. But now if you switch from the E bar to the D bar, which is the zero electric displacement, you can see that the polarization relaxed almost instantaneously to the target value. And then this actually provides confidence, telling us the method actually can work. Then what you can do is you actually can switch on your proton charge and look at how the polarization would evolve all the time. Then from there, you actually can plug into the formula which I show and get your capacitance. So we did that for the TiO2 system, and the number which we get is between 80 to 100 microfarad per centimeter squares, which agree quite well with the experimental value. And we also extend the study together with a colleague from Xiamen to look at the cassiteride tin oxide system, which is isostructure of TiO2, but with a characteristic dissociative water absorption. So I'm not going to give the details about actually the work. And so in addition to the metaloxides, we're also using the same methodologies to look into the ionic, polar ionic crystals, as well as the liquid water. And also colleagues from other places, they actually use it to look at other type of systems. So most of this study was summarized in this topic review that we have published a couple of years ago. So in that topic review, which one thing which we have mentioned is that what we should do next is actually to combine the finite field method with the machine learning. And we also heard a nice talk yesterday which shows the development, try to couple the external fields to the molecules to look at the spectroscopic data. And then for us, the focus is, from beginning, is on the modeling of electrochemical interface. And for that purpose, so we have developed this Python package, which is called PiNN. So we implement both the beta PiNN neural network and also our graph convolutional neural network variant, which is called the PiNN. So the code can try to fit the potential energy surface, as every code can do. And also we can predict the dipoles for both isolate and also the condensed phase system, as a number of codes can do. And what is unique for the PiNN is that we also try to build a machine learning model which can give you the response function. And that is needed, as you see in a moment, for describing electrified interface. So this response function is called the charge response kernel. So this describes how actually the electronic densities would change in response to external field. So it's a long local function, as you can see here. So this chi, the response kernel, need to satisfy a few symmetric constraints. For example, we know that it's a symmetric matrix. In addition, that each row and each row, when summed together, it has to be 0 to make sure that you actually satisfy the charge constraint. And then the question for doing machine learning model is to see, can we actually find out sort of good targets which you can use the local descriptors to produce this chi matrix. Because as we know that the big success of the atomic machine learning so far is relies on local descriptors. And then we are going to take some priors from the chemistry of physics. So if you're a chemist, you might be familiar with so-called the Berkowitz power identity, which try to connect so-called the softness kernel, so this eta inverse, to the response kernel. And if you are a physicist, you're more familiar with so-called Dyson equation, which try to connect this irreducible response kernel, the Chi-S, for the non-interacting system, to the final response kernel Chi. And why actually I'm going to mention this sort of intermediate quantity? Because this intermediate quantity, they are actually nearsighted. So it's shown by the conceptual DFT group in Belgium. So the softness kernel, this eta inverse, is actually nearsighted. So it's shown for this molecule, when you do this alchemical transformation from carbon to nitrogen, you can see that the linear response kernel is actually long-range quantity, where the softness kernel is actually short-range quantity. And the same applies for this irreducible response kernel, Chi-S. As shown by De Yulu at Brookhaven National Lab, the Chi-S is also a short-range function and satisfies this near-side principle. So this provides actually physical base for us to build our response kernel based on the local descriptors. And now we have the strategies, right, to build a machine learning model. Next question is which kind of data we can use to actually generate this kernel. And we know that when you talk about the polarizability, there is two common ways to compute. So you can compute with finite-field methods. You can also compute with so-called sum of states. And then there are actually a third way. Actually, you can also get your polarizability, which is through the linear response kernel. So this was actually shown by Anthony Stone a long time ago. And the nice thing of this formulation is that your response kernel is still a scalar quantity. But by using this formula, the resulting polarizability actually satisfies the translational and the permutational invariance, and also the rotational covariance. So now we have all the ingredients. So we implement these different flavors of the model, as you can see here, by taking the ondas from the conceptual DFT. So you have the conventional so-called EM model, which built on the hardness kernel. And also we have this eta inverse, which gives you the direct prediction of the softness kernel. And then we also did this local version of the Chi, which basically do a decomposition of your Chi into atomic contribution, as what you usually do for the total energy when you come to the machine learning potential. And then we also implement this ACKS2, AX2, which stands for the atom condensed constant approximate to the second order. And all these kind of different flavors would lead to this Chi matrix, which you can use polarizability data to parameterize. And once you have the Chi, the nice thing of it is that now you actually can apply external potential or external field. So you can generate your response charge, as we have listened from talk this morning. And one thing I want to mention is that also we show in paper is that in fact the AX2 is just equivalent to the Dyson equation. So instead of solving a larger matrix, you actually can solve a smaller matrix and get the same result. And then since our data, we try to produce the Chi is using polarizability. So the question is how good the model is when it comes to predicting the polarizability tensor. So here I'm showing you is the result. So the result depends on which model you're using. And nevertheless, you actually can reach the accuracy per atom for the polarizability, which is about 0.1 atomic unit. So if you're like the Ångström, the cubic, then it's about 0.01, which is quite accurate for this model. And then you can also look at how the polarizability scales with the size of a molecule. Because we know that one of the classical problem with the EM model is that it has this superlinear scaling with the size of the molecules for the linear alkane system. And we show here is that, in fact, you can use the data to fix this problem. So this is one nice observation that we made in our work. And second is that if you complete it using local model, which is this decomposition of the Chi into atomic contribution, then this local model actually does not scale with the size of molecule for the conjugate system, which is not a surprise because for the conjugate system, your electrons are delocalized. And then once you're actually able to using polarizability to build up your Chi matrix, Now what you can do is you actually can apply the electric field to look at how the response of the molecule looks like. So here I'm showing examples of the propylene carbonates, which is the common used solvent molecules. And you can see that our response kernel actually can give a quite reasonable the charge distribution as compared to the reference response density, which is density difference between the one which under the field and without. And so these are for the small molecules, but it's not limited to small molecules. You actually can easily extend this to do the periodic bonding systems. So here I'm showing the examples of the graphene. You can actually put the point charge which is next to a graphene sheet and see how actually your system would respond to the external perturbation. And then you can see where I'm going, is that we actually can do this for the electrified interface. So when it's come to the model, the polarizable electrode, the most popular model is so-called the Sprigg-Shipman model. And so this model was quite used a lot for modeling different type of supercapacitors. And then recently, this model has been extended to include so-called Thomas Fermi screening lens for the electrode, which allowed you to investigate the different metallicities in the electrode and how that would influence your energy storage. But nevertheless, the setup of the Sprigg-Shipman model is limited to the single element system, which means that you cannot really do heterogeneous electrodes, which is much more useful when it comes to the materials design. And this motivates us to actually develop this so-called pinwheel interface. So how the pinwheel works? So in this pinwheel interface is that you have electrode and electrolyte interface, and then you pass this electrode structure to the pin. And pin will generate the response kernel, and also you will generate the base charge before actually the perturbation. And then you pass the information to the metal wall code, which you heard from this morning. That is co-developed by the Phoenix groups at Paris for modeling electrochemical system. And then by combining these informations and also taking now the external potential, which due to your electrolyte, your solvent, as well as your external bias, they actually can compute the response charge, which will generate at your electrode surface. And then you can propagate the dynamics by computing the electrical interactions between these two. And this allows us to look at a functionalized graphene oxide surface. So here I'm showing you the examples where you have the hydroxyl terminate, the graphite. So you can see that when you increase the surface coverage, there is actually a large increase of the capacitance. And this is not a surprise because when you're increasing the surface hydroxylations, then it increases the hydrophilicity of surface. So your capacitance actually becomes larger. And what's interesting is that now you actually can play with the model. So you can actually see how the surface roughness and atomic polarizability will contribute to the capacitance. So you actually can switch off your kernel and use original metal wall kernel and treat all the carbon as atoms as carbon. You can see that this blue line, these green lines, which show a much enhanced capacitance. That is due to the surface roughness. And if you actually use the kernel properly, and now you can see that the capacitance is much more reduced because we know that the polarizabilities of the hydrogen is much smaller compared to the carbon. So you can actually disentangle this effect for a realistic system. And then you can do something more. It's because we know that for the reduced graphene oxide, you would have the surface carboxylate group. And this group usually have a pKa, which is about 6, which means when the surface in contact with water, then this carboxylate groups will deprotonate it. You will have negative charge there. And now we actually can simulate such a system with the pinwheel interface. And you can actually apply different potentials and try to find out at which point the surface electrode charge will be 0. So this will corresponding to so-called the point of zero free charge. And then at this point, you can also compute how much the capacitance is due to the proton charge. And what we find out is that this capacitance due to the proton charge is much larger. It's about like 100 microfarad per centimeter squared, which is rather comparable to the one which I showed you before using the DFTMD simulation that we did for the metaloxide system. So with the pinwheel, you actually can look at heterogeneous electrode, which is very nice. But this is still sigma strict model, which means that this is the semi-classical model. So the question is, can you really do metallic system with the finite field, the DFTMD? So the short answer is yes. That's the example I'm showing here, which is the gold 100 sodium chloride electrolyte interface. So you can get the stable dynamics from the constant D simulation. And from there, you can compute the capacitance, which is about 40 microfarad per centimeter squared. That is rather comparable to experiments. But there are a number of caveats to running such a type of simulation. So we are in the stage trying to finalize this work. And once that is done, it's actually opened the door for a number of things, because we can also look at conducting oxide, in addition to the insulating oxide, which I showed you at the beginning. And also, it will provide the necessary reference data for us to parameterize a machine learning model. So with that said, thank you very much for your attention.
Thank you. Time for questions. Anything? Anybody? I could start with a question. So you had quite short MD simulations, 15 picoseconds in the beginning of the talk, but you showed that the properties were converged despite this ion diffusion that happens.
Right. So there are two answers to two aspects for the answers. One is that when we actually build up double layers, we leverage on the classical molecular dynamics simulations, try to bring the ions is more close to the surface. So this actually saves you a lot of time. And second is that because you actually switch the electric boundary conditions, the relaxation time of the polarization is speed up. And this is actually due to so-called the Debye series of dielectric relaxations, which Debye showed that if you switch from the constant potential to the constant charge, then the dipolar relaxation will speed up by the dead constant of the system. And for the ecosystem, it's the equivalent to a 2-order magnitude speed up. And that is the piece of physics we explored here to speed up the simulation. Yeah.
Then I think we thank the speaker once more.